Hello, we are Group 5, and this video will outline the motivation, objective, theory, procedure, and results of the Chemical Vapor Deposition Lab. Chemical vapor deposition, or CVD, is an industrial coating application method. It is used in industries worldwide. Some examples of these industries include the aerospace industry, the medical industry, the semiconductor industry, and the glass coatings industry. CVD is part of many processes as well, such as graphene production and carbon nanotube production. There are many objectives of this lab. The first is to determine how the substrate temperature impacts the reaction rate. This was done by varying the chiller temperature between 10 and 20 degrees Celsius. The next objective is to determine how the ratio of hexyl acrylate to tert butyl peroxide impacts the reaction rate. In our experiments, we used a ratio of 4:1, 4:2, and 4:3. The next objective was to use theoretical equations to determine the activation energy of the polymerization reaction. Finally, we were asked to coat a sample for Dr. Willis's research lab. In order to complete the calculations for this experiment, we started by finding the angle of refraction for the laser. The cosine of this angle was found by taking the square root of 1 minus the sine of theta 1 divided by the index of refraction squared. Theta 1 is the angle that is described in the picture below. Now we can find the amount of feed deposited on the sample by dividing the wavelength of the laser by 2 times the refractive index times the cosine of theta 2. In our case, the wavelength of the laser is 633 nanometers, and the refractive index is 1.428. Next, the rate can be calculated by multiplying the change in coating thickness per sinusoidal cycle by the number of sinusoidal cycles recorded on the iLab program, and then dividing that by the total time of the trial. Finally, the activation energy can be calculated using the last 2 equations. In the first of these equations, you solve for delta H. In this equation, R is the constant 8.314 joules per mole Kelvin, and T is the temperature of the substrate. You can then multiply that delta H by -2 to get the activation energy.
The second part of the experiment is to coat a sample with a thickness of approximately 100 nanometers. To determine the point at which 100 nanometers is deposited, the intensity is found using the equation listed. I over IO is a value of 0.2, while I max is the maximum intensity found in the experiment. first variable tested was the change in chiller temperature. The natural log of deposition rate was plotted against the inverse chiller temperature, showing that as chiller temperature decreased, the deposition rate increased. The reason for this is because the activation energy was found to be negative 11 kilojoules per mole. Since the reaction is exothermic, the deposition rate increases as energy is removed. The next variable tested was the amount of tertiary butyl peroxide. The general trend is that as TBPO increases, the reaction rate also increases. This is because TBPO is a peroxide initiator that promotes polymerization. The experiment was successful in depositing hexoacrylate onto the silicone wafer. To summarize, our activation energy was found to be negative 11 kilojoules per mole, while literature values show negative 41 kilojoules per mole. This is most likely due to correlations being slightly inaccurate and does not show all the constants needed. Furthermore, a decrease in chiller temperature and an increase in TBPO shows an increase in deposition rate. Since ratios of 4:4 and above were not tested, this conclusion may not be completely accurate and further testing will be needed.